Welcome to the second training package in the series of electronic fuel injection and engine management programs. This package covers the principles of operation of the Delco engine management system and is based on the system as fitted to the VN Commodore port fuel injected V6 engine. Also included in this video training package are segments on throttle body injection as fitted to JD Camira and LD ASTRA. This program also covers catalytic converters and oxygen sensors. For maximum benefit, the video should be used in conjunction with the Leader's Guide and Participant Study Guide included in this package. The Participant Study Guide in particular will also assist in noting some of the variations in specification on certain models. If not familiar with electronic fuel injection at all, it would be advisable to view the basic P.F.I videotape in the Engine Management 1 package. There will be times in this presentation when you will see this picture appear. These breaks have been inserted to allow you to review the material you have just seen. We suggest you follow the instructions on the picture to fit your particular meeting and level of understanding. Oh, by the way, I've got my younger brothers and cousin to pop in and out of a few segments to help give a more complete outline on the operation of this system. Engine Management System. Welcome to the Engine Management section of this tape. In this section, we'll be looking at all the features and functions that control the Holden 3800 V6 engine. First of all, a little history. The Engine Management System is based upon the GMP4 engine control module from Delco Electronics. The GMP4 engine control module, or ECM, was first used by Holdens in the 1986 JD Camira 1.8 litre throttle body injection engine. Then in 1987, JE Camira 2 litre port fuel injection engine. In 1988, it was used on the ASTRA 1.6 and 1.8 litre engines and was also introduced on the Commodore V6 and V8 P.F.I engines. Basic engine functions. Now we'll proceed to the basic engine function descriptions. Some of the main features of this engine are simultaneous multi-point port fuel injection, electronic spark timing with knock control, analog backup system for limp home, and ancillary controls such as fuel pump, cooling fans, air conditioner clutch, torque converter clutch control, and built-in diagnostic system. All these engine management functions can be broken down into the following areas: fuel injection control, electronic spark timing, idle speed control, fuel system control, cooling fan control, torque converter clutch control, and air conditioning control. To show you where all these sensors and actuators are on the vehicle, come with me on a tour of the VN 3800 V6 components and their locations. The components will be discussed in greater detail later. Input sensors. Throttle position sensor is here on the throttle body. Coolant temperature sensor is at the rear of the inlet manifold. The manifold air temperature sensor, or MAT, is located at the inlet runner of number 6 cylinder. Manifold absolute pressure sensor, or MAP, is on the left-hand side of the firewall of the vehicle. The crank reference pulse sensor is behind the harmonic balancer. The knock sensor is on the front right-hand side of the engine block. The oxygen sensor is located at the left-hand branch of the exhaust manifold. Park neutral switch is under the T-bar console. Vehicle speed sensor is in the instrument cluster, and the air conditioner request signal is via the wiring harness. The 4th gear discrete switch and over temp switch is located in the automatic transmission. So much for the inputs. Now let's run through the outputs. Output actuators. The fuel injector solenoids are here, in the inlet manifold. The direct fire ignition module is on the front left-hand rocker cover. The idle air control motor is on the throttle body. The engine cooling fan, the fuel pump, and the air conditioner compressor clutch relays are all on the relay bar in the engine bay. Check engine light is in the instrument cluster. The oil pressure switch is on the right-hand side of the engine block. The engine control module, ECM, and the ALDL connector are located in the left-hand side kick panel area. The torque converter clutch solenoid is in the transmission. Fuel injection controls. We'll start by looking at the fuel injection control. The electronic control module, or ECM, is a microcomputer which monitors or controls all the output functions.
The brain of the ECM is the microprocessor, which performs all the mathematical and logical functions of the unit. The microprocessor monitors input signals from the sensors and can send commands to the engine to control a number of functions. In addition, the microprocessor has the ability for self-diagnosis and to notify the owner and technician of possible system problems by means of the check engine light. Before the microprocessor can function, however, it must follow instructions stored within the ECM's memory system. These memory systems are contained within a single unit, called a memcal, or memory calibration. As the memcal unit is programmed for a particular vehicle specification, it has been designed to be a replaceable component within the ECM. Naturally, care must be taken to prevent physical damage if the memcal unit has to be replaced or installed in a replacement ECM. In addition, the correct memcal unit must be selected to suit the particular vehicle's equipment specifications.
Power supply.
As with all ECMs, a power supply and inputs from various sources are required before any output can result. Let's look first at the power supply. Battery voltage is applied directly to the ECM via a fusible link. That is, the ECM is live at all times, even with the ignition key removed. This very low current supply is necessary to provide continuous power for the ECM memory. There is also battery voltage applied via the ignition relay circuit when the switch is in the on or start positions. A closed circuit is achieved by separate earth returns through the engine block.
The fuel injector solenoids are all connected in parallel and are under the control of the engine control module, or ECM. The injectors are simultaneously fired once every crankshaft revolution. That is, after every reference pulse received from the ignition system. The ECM bases its calculations of the required pulse width using the following inputs. Throttle position sensor, manifold absolute pressure sensor, manifold air temperature sensor, coolant temperature sensor, engine speed, vehicle speed sensor, oxygen sensor, starter signal, park neutral switch, and battery voltage. Throttle position sensor. Mounted on the throttle valve shaft, the throttle position sensor, or TPS, is a variable resistor or potentiometer. The ECM supplies a 5-volt reference power supply to the TPS, then measures the variable voltage signal from the sensor, using this input signal to compute the percentage of throttle opening. At closed throttle, the output voltage is approximately 0.9 volts, whereas at wide open throttle, the voltage increases to approximately 4.5 volts. Manifold absolute pressure sensor.
The manifold absolute pressure sensor measures the changes in the intake manifold pressure which result from variations in engine load and speed. The MAP sensor, working on a reference 5-volt power supply from the ECM, monitors variation in manifold pressure, changes its output voltage accordingly and sends it back to the ECM. Previously, intake manifold pressure has been expressed as vacuum and measured in millimetres of mercury. It is convenient to now use the term absolute pressure. It works like this. Most pressure gauges we have used in this country have always registered 0 when not connected. In actual fact, though, atmospheric pressure has still been applied to the gauge, but it has been calibrated this way for convenience. This type of gauge reading is referred to as gauge pressure. Reference to this graphic will show you what I mean. Everything above the atmospheric line is referred to as gauge pressure, and everything below the atmospheric line has been referred to as vacuum, down to a point where a perfect vacuum was achieved. If we were to start from this perfect vacuum point, though, and take our pressure reading from here, then an absolute pressure reading would be achieved. In this way, not only is it easier to understand the system operation, it also allows the ECM to monitor changes in atmospheric pressure, which can occur with normal vehicle operation in different parts of Australia. To help still further, look at this gauge. The first thing you will notice is that the needle is showing a reading, even though the gauge is not connected to anything. This gauge is an absolute pressure gauge, and it reflects changes in the atmospheric pressure in a similar way to a barometer.
Manifold air temperature sensor. The manifold air temperature, or MAT sensor, is mounted in the inlet manifold runner. Electrically, its operation is similar to the coolant temperature sensor, but since it is required to sense the temperature of air and not liquid, its construction differs at the tip area. Whereas the coolant temperature sensor has a solid tip which covers its thermistor, the MAT sensor thermistor is protected from physical damage by a screen. The function of the MAT sensor, as the name suggests, is to inform the ECM of the air temperature within the inlet manifold. A change in air temperature within the manifold will cause a resistance change within the sensor, which varies the voltage signal to the ECM. A voltage signal of about 4 volts indicates the air is cold, and an increase in injector pulse width is required to enrich the air-fuel mixture. A voltage signal of about 1 volt indicates the air is hot, and a decrease in injector pulse width is required to lean off the air-fuel mixture. Like the coolant sensor, the MAT sensor receives a 5-volt supply through a reference resistor internal to the ECM. By passing current through the sensor's variable resistance, a voltage signal is returned to the ECM, where it is used to help in calculating the injector pulse width. Coolant temperature sensor. The coolant temperature sensor is a thermistor. That is the term used to describe a temperature-sensitive resistor that varies its resistance in proportion to the temperature. The CLT changes its resistance with changes in temperature in a negative coefficient manner. That is, the sensor's resistance falls as the temperature rises. Engine speed. The P.F.I dual crank sensor contains 2 Hall effect switches with 1 shared magnet mounted between them. The crankshaft sensor is mounted in a bracket bolted to the front of the cylinder block near the crankshaft balancer. The interrupter rings are located and mounted to the rear of the crankshaft balancer assembly. The interrupter rings pass through the slots in the crankshaft sensor and provide RPM information to the ECM. Vehicle speed sensor. The vehicle speed input to the ECM comes from the instrument assembly via the speedometer circuit for driver road speed information. The speedometer circuit is supplied with 10 earthed pulses per revolution from an electronic Hall effect sensor driven by the transmission output shaft. The electronic divide by 5 circuit in the instrument assembly then changes the pulses to 2 per revolution and sends them to the ECM. Battery voltage. The ECM constantly monitors battery voltage and corrects system outputs accordingly. This monitoring and correction function is necessary for the optimum operation of the fuel pump, injectors and the idle air control motor. Oxygen sensor. The oxygen sensor input is only used for closed-loop calculations. Let's look at this in more detail. When the engine is started, with the RPM above 350 and the engine is idling, the ECM will operate the fuel control system in the open-loop mode. In open loop, the ECM calculates the air-fuel ratio injector pulse width based on all the inputs except the oxygen sensor input signal. That is ignored. The system will stay in the open loop mode until the following conditions have been met. The oxygen sensor must be in the ready condition. The coolant temperature is above 44 degrees Celsius and the engine must not be at idle. This stage of ready requires some explanation. When the oxygen sensor is cold, its internal resistance is extremely high and it does not generate any voltage. As it heats up to approximately 360 degrees Celsius, its internal resistance decreases and it begins to generate a voltage. It is now in a ready state. Since either one can be the last to occur, the time at which closed-loop operation occurs can vary from a few seconds to a few minutes from engine startup. For instance, if the engine had not been run for several hours, the oxygen sensor ready would occur first. Then, when the engine has eventually warmed up to above 44 degrees Celsius, closed-loop operation will begin. If this engine was running, fully warmed up, shut off and then restarted, it would only take a few seconds before closed-loop operation starts. Starting at the top of our loop, with a richer mixture, meaning less oxygen in the exhaust, we have a high sensor voltage to the control module. The ECM then decreases the injector pulse width, creating a leaner mixture, meaning more oxygen in the exhaust. The low sensor voltage to the control module increases the pulse width. This cycle goes on continuously to achieve an average air-fuel ratio of 14.7 to 1, provided the ECM is running in the closed-loop mode. The base pulse width is still calculated by the ECM from information received about manifold pressure, air temperature, coolant temperature and engine speed. The addition of the oxygen sensor allows us to more precisely fine-tune the amount of injected fuel based on what is sensed in the exhaust stream by the oxygen sensor. The oxygen sensor then sniffs the exhaust gases, and if the oxygen in the exhaust is too little or too much, a correction factor is added to the base pulse width calculations, thus the term closed loop. This system permits a very accurate supply of fuel to maintain the air-fuel ratio very close to the chemically correct proportions of 14.7 to 1. Maintaining the air-fuel ratio within a very close tolerance of 14.7 to 1 not only provides good fuel economy and excellent drivability, but also helps to keep the three-way catalytic converter operating within the range above 80% efficiency. There are obviously some operating conditions that would require an air-fuel ratio other than 14.7 to 1. Cold start, acceleration and power situations require some form of mixture enrichment, while deceleration and clear flood call for a leaner mixture. During these conditions, the loop is broken and the oxygen sensor input is ignored by the ECM. Starter signal. When the key is first turned on, the ECM will turn on the fuel pump relay and activate the pump for 2 seconds. In that time, the pump will build up pressure to the injectors. The ECM checks the coolant temperature sensor and the throttle position sensor to determine the proper air-fuel ratio for starting. Park neutral switch. The park neutral switch input is used by the ECM to compensate for a change in engine load whenever the automatic transmission is shifted into any range other than park or neutral. This is to ensure that the correct idle speed is maintained. Fuel system. The fuel control system starts with the fuel in the fuel tank, and the pump provides pressurized fuel to the fuel rail, where the pressure regulator keeps the pressure at a constant 250 kilopascals above inlet manifold depression. Fuel in excess of injector needs is returned to the fuel tank by a separate return line. Fuel pressure regulator. The pressure regulator is a diaphragm-operated relief valve with fuel system pressure on one side and manifold and spring pressure on the other. The function of the regulator is to maintain a constant pressure above inlet manifold pressure at all times by controlling the fuel flow to the return line, thus working as a calibrated bypass. Fuel pressure is regulated at 250 to 270 kPa. Fuel which is not used by the injectors passes through the pressure regulator before being returned to the fuel tank. Fuel injectors. The fuel injectors are solenoid-operated fuel flow valves controlled by the ECM. The ECM energizes the solenoid, which lifts the normally closed needle valve off its seat. The fuel, under pressure, is injected into the intake port area of the cylinder head just above the inlet valve. They use a plate with 4 minute holes that direct 4 jets of fuel down towards each other in such a way that the jets collide and break up to give a cone-shaped spray. This spray pattern results in maximised combustion efficiency, improved power, improved fuel economy and lower exhaust emissions. Fuel system control. The ECM turns on the fuel pump via a relay for 2 seconds following ignition switch on or following a reference pulse from the ignition system. So to maintain fuel pump operation, the ECM must see a reference pulse from the ignition system. The oil pressure switch will also turn the fuel pump on when a sufficiently high oil pressure is detected. This is for the analog backup system operation in case the ECM fuel pump circuit fails. As can be seen from this wiring schematic, the oil pressure switch is connected across the relay switch contacts as a fail-safe feature. In the event of an ECM or relay malfunction, the fuel pump will be switched on when the engine oil pressure switch contacts close. The switch will then be responsible for fuel pump operation, but engine cranking time to start may be longer than normal. Remember, this feature could assist in a relay failure diagnosis. Fuel injector operating modes. The fuel injection operation could be defined in the following modes. 1. Synchronized injection. 2. Acceleration enrichment. 3. Deceleration enleanment. 4. Battery voltage compensation. 5. Fuel cutoff mode. And 6. Clear flood mode. Let's look at each mode briefly. Synchronized injection. The fuel injector solenoids are all connected in parallel and are under the control of the engine control module, or ECM. The injectors are simultaneously fired once every crankshaft revolution, that is, after every reference pulse received from the ignition system. As the control unit receives each input, it evaluates the information and provides an electrical pulse to the injectors. The duration of the pulse controls the amount of time the injectors stay open. The opening time is controlled and varied by the control unit to provide an optimum quantity of fuel according to the engine requirements. Acceleration enrichment mode. The ECM looks at rapid changes in throttle position, TPS, and manifold pressure, MAP, and provides extra fuel for power and smooth acceleration. There are 2 modes in which the fuel injectors can operate. The first mode used under most conditions is called synchronous fuel delivery. The injectors are pulsed in time with ignition pulses, 1 per crankshaft revolution. Asynchronous fuel delivery is used when extra fuel is required for power, called acceleration enrichment. The ECM will pulse the injectors independently of ignition pulses, and as often as once every 6.25 milliseconds if required. Notice that this is based on a time interval and not in unison with ignition pulses, thus the term asynchronous. The following conditions must be met before the ECM will go into the asynchronous mode of operation. First, when the pulse width or injector on time is too small for fuel to be delivered accurately by the injector. The second time that the asynchronous injection is desirable is under acceleration enrichment. Deceleration enleanment mode. When the manifold pressure is suddenly reduced again, the ECM looks at changes in throttle position, TPS, and manifold pressure, MAP, and reduces the amount of fuel by decreasing the pulse width. When decelerating, a leaner air-fuel mixture is required to reduce emission levels of hydrocarbons and carbon monoxide.
Fuel cutoff mode. We have 3 different modes in fuel cutoff. 1. Deceleration fuel cutoff. 2. High RPM fuel cutoff. 3. Ignition cutoff. First, let's look at the deceleration mode. When deceleration is rapid, that is a warm engine and the throttle is shut, the ECM can cut off the fuel for short periods at a time.
The fuel cutoff mode occurs when all these conditions are met. Coolant temperature above 56 degrees Celsius, engine RPM above 1500, vehicle speed above 35 kilometres an hour, throttle is closed, park neutral input indicates in gear, auto only, and the MAP input indicates no engine load, less than 20 kPa. High RPM cutoff occurs at 5,400 RPM and will continue to cut off the fuel delivery from the injectors until a safe RPM at 5,000 occurs.
This protects the engine from any mechanical damage that may occur from over-revving. Ignition cutoff prevents any fuel from entering the engine and stops dieseling.
Clear flood mode.
With the clear flood mode, the ECM detects that the driver is trying to clear a flooded engine if cranking the engine with the throttle wide open. In this case, the ECM reduces the fuel delivery to an air-fuel ratio of 20:1. Battery voltage compensation mode. When the battery voltage is low, the injector mechanical movement takes longer to open, and the ignition system may deliver a weak spark. The ECM will compensate by increasing the injector pulse width, increasing ignition dwell time, and increasing the idle RPM.
Controls. Idle speed control.
The ECM has full control over idle speed via an air bypass valve operated by the idle air control stepper motor. The idle speed cannot be adjusted manually. The idle air control stepper motor has a very wide control range. At no load, the engine speed can be controlled from about 500 RPM to about 2500 RPM. This allows the stepper motor to compensate for large load variations, such as the air conditioner compressor clutch engaging, alternator loads, and automatic transmission drive selection. The input sensors used to control idle speed are throttle position sensor, manifold absolute pressure sensor, coolant temperature sensors, engine speed RPM, vehicle speed, air conditioner clutch, park neutral switch, and battery voltage. By extending the pintle to decrease the airflow or retracting the pintle to increase the airflow, a controlled amount of air can bypass the throttle valve. If engine speed is too low, more air is bypassed around the throttle valve to increase the RPM. If engine speed is too high, less air is bypassed around the throttle valve to decrease RPM. The IAC valve moves in small steps, numbered from 0 for a fully extended pintle to 255 with a fully retracted pintle. During idle, the required position of the IAC valve is calculated by the ECM based on battery voltage, coolant temperature, engine load, and actual engine speed. If the engine speed drops below 600 RPM and the throttle valve is closed, the ECM senses a near stall condition. The ECM will then calculate a new pintle position to prevent stalling. If the IAC valve is disconnected or connected with the engine running, the ECM may lose track of the actual position of the IAC pintle. In this case, the IAC will be reset to the ECM's desired idle RPM when the engine speed is raised above 2000 RPM. The IAC valve affects only the idle speed of the engine. If it is open fully, too much air will be allowed into the manifold and idle speed will be too high. If it is stuck closed, too little air will be allowed into the manifold and the idle speed will be too low. A good example of the stepper motor in operation is when the air conditioner compressor clutch is to be engaged and the engine is in an idle condition. The ECM will receive a signal from the air conditioner switch to turn on the air conditioner clutch. Before engaging the clutch, the ECM will adjust or increase the engine RPM a number of steps. This will prevent the engine from stalling or sagging. Another function that the idle control system will perform is if the throttle is suddenly closed, an increase in hydrocarbon emissions is caused by the sudden decrease in manifold pressure. To prevent this, the ECM simulates a dashpot sensation by increasing the bypass air rate, then gradually decreasing it to cushion the effect of a rapidly closing throttle blade. Cooling fan controls. On VN, only one engine cooling fan is required to look after the engine's temperature. It's controlled by the ECM. Let's go into some more detail and find out when the cooling fan is turned on or off. First, the engine cooling fan will be on when the coolant temperature is above 101 degrees Celsius, the air conditioning is on, if the check engine light is on, or when the vehicle is in diagnostic mode. The engine cooling fan will turn off when the engine coolant temperature is below 95 degrees Celsius, when the air conditioning system is off, when the vehicle speed is above 55 kilometers per hour, and when the vehicle is in standard trim and the check engine light is off. Torque converter clutch control. The torque converter clutch control is based on the following conditions. Throttle position sensor must be above 4% of throttle opening. Coolant temperature sensor above 44 degrees Celsius. The vehicle speed above 75 kilometers per hour, or when the fourth gear discrete switch and the overtemp switch are closed. Air conditioning control. Air conditioning is next, and again the ECM plays a large part in its operation. The ECM delays the air conditioner compressor clutch engagement for about 0.5 of a second while it boosts the idle speed to allow for the extra load onto the engine. This ensures smooth idle. The air conditioner compressor clutch disengages for the following conditions. It is a stall saver to prevent the engine from stalling. Wide open throttle. It turns the clutch off for the extra power that may be needed, especially when overtaking another vehicle on the highway. High RPM. That is, to save the compressor from damage due to the RPM being too high. Direct fire ignition system. The ignition system for the VN Series V6 engine is a distributorless direct fire ignition system, better known as the DFI ignition system. This system is unique as it uses a waste spark method of spark distribution. Sounds strange, doesn't it? Well, what does it mean? Let's start from the beginning. The direct fire ignition system does not use a conventional distributor and ignition coil. Instead, the DFI system consists of 3 ignition coils combined to form one coil pack, a DFI ignition module, a dual Hall effect crankshaft position sensor, an engine harmonic balancer with crankshaft interrupter rings mounted on the rear of the balancer, and the electronic spark timing, or EST portion, of the electronic control module, better known as the ECM. The DFI ignition system has several advantages over a mechanical distributor. More compact mounting, the elimination of mechanical timing adjustments, less maintenance, no mechanical load on the engine, increased available coil saturation time or dwell time, and longer coil cooldown time between firing events. Let's have a look at the DFI ignition system's operational components and their locations. The DFI coil pack and ignition module assembly is located here on a bracket attached to the front left-hand cylinder head. The coil pack is serviced as a unit. The coils operate in the same manner as a conventional ignition coil. Each coil provides the spark for 2 spark plugs simultaneously. The ignition module is located under the coil pack and is connected to the ECM by a 14-pin wiring harness connector. The ignition module controls the primary circuit to the coils, turning them on and off. Also, anything below 450 RPM, the DFI ignition module controls the ignition by triggering each of the 3 coils at predetermined dwell and advance figures based on engine speed only. This is called module mode ignition. The ignition module is non-repairable. That means if the module does fail, it is replaced as a whole unit. Do not try and repair this item. The DFI dual crank sensor contains 2 Hall effect switches with 1 shared magnet mounted between them. The crankshaft sensor is mounted in a bracket bolted to the front of the cylinder block near the crankshaft balancer. The interrupter rings are located and mounted on the rear of the crankshaft balancer assembly. The interrupter rings pass through the slots in the crankshaft sensor and provide timing information to the ECM. Let's have a look at the way this works in more detail. The windows in the interrupter rings activate the Hall sensors as they provide a path for the magnetic field between the sensor's transducer and the center-mounted magnet. When the Hall effect sensor is activated, it earths the signal line to the ignition module, pulling the crankshaft signal line's applied voltage low. Then, as the tooth enters the Hall sensor, the signal goes high. This generates a square wave RPM signal. The outer interrupter ring has 18 10-degree windows and 18 10-degree teeth. The inner ring has 3 windows, each of a different width. The first window is a 10-degree window, the second a 20-degree window, and the third a 30-degree window. With the rotation of the interrupter rings through the Hall effect sensors, the combination of the sensor's output signals uniquely identify each of the 3 cylinders' pairs at a specific point in the crankshaft rotation. The crankshaft sensor is not adjustable for ignition timing, but the positioning of the sensor in the interrupter rings is very important. The clearance between the crankshaft sensor element and the interrupter rings is measured here.
check your current service literature for correct specifications. Waste spark theory. With the DFI ignition system, each end of the coil secondary is attached to a spark plug. These two spark plugs are on companion cylinders. That is, cylinders that are at top dead centre at the same time. When the coil discharges, both plugs fire at the same time to complete the series circuit. The one that is on compression is said to be the event cylinder, and the one on the exhaust stroke, the waste cylinder. Since the polarity of the primary and secondary windings are fixed, one plug fires in a forward direction and the other in reverse. This is very different to a conventional ignition system, which fires all plugs in the same direction each time. Because of the demand for additional energy, the coil design, saturation time and primary current flow are also different. This redesign of the system allows higher energy to be available from the ignition coils, greater than 40 kilovolts at all RPM ranges. The Holden V6 has a firing order of 1, 6, 5, 4, 3, 2. Each cylinder is paired with its opposing cylinder in the firing order, so that one cylinder on compression fires simultaneously with its opposing cylinder on exhaust stroke. Since the cylinder on the exhaust stroke requires very little voltage to fire its spark plug, most of the voltage is concentrated on the cylinder which is coming up for compression. To begin with, we will concentrate on cylinders 1 and 4, companion cylinders. The ignition system is unaware of and has no need of sensing which of these two cylinders is on compression. When the coil fires, one plug fires forward and the other fires backward simultaneously. The voltage dropped across each plug is determined by the polarity and the cylinder pressure. The cylinder on compression will require more voltage to create an arc than the one on exhaust. Electronic spark timing. With the electronic spark timing, the ECM calculates the spark advance and dwell time for the ignition system module based upon its inputs from the following sensors: throttle position sensor, manifold absolute pressure sensor, coolant temperature sensor, engine speed RPM, ignition switch, and knock sensor. It's time to look at the next major output from the ECM, and that is electronic spark timing, or EST. The purpose of EST is to maintain the best spark timing under all conditions of engine load and speed. In addition to providing the control for spark timing to optimize performance with minimum emissions, the ECM also controls the dwell period over the engine operating speed range. This allows the ignition coil the correct time to build up the magnetic flux density necessary for the generation of the high-energy spark. Operating modes. There are two system operating modes: a bypass or module mode and an EST mode. Bypass or module mode. When reliable ECM operation of the spark timing cannot be guaranteed, the bypass mode will be in operation. This will occur when the engine is stopped, cranking, or if an EST system fault has been detected by the ECM. During this time, both spark timing and dwell control at the base level are controlled by the ignition module. EST mode. Once the ECM detects an engine speed of above 450 RPM, it will energize the ignition module bypass terminal to a value of 3 to 5 volts. This action then gives the ECM control of the spark timing and the dwell period. The actual spark timing is determined from inputs received and referenced to the calibration of the MEMCAL unit in the ECM.
The spark advance signal is then sent to the ignition module via the EST circuit. Dwell control. Dwell period is achieved by the ECM's control over the length of time the signal is sent to the ignition module. This time is maintained long enough for the primary current to build up the coil saturation or flux to achieve an optimum secondary discharge. When primary current flow through the coil is interrupted, the collapse of the magnetic flux causes an induction of high energy voltage in the secondary windings. This, of course, is normal ignition coil operation. It can then be seen that the actual spark will be generated as the ECM signal to the ignition module stops. Knock sensor. The electronic spark control or ESC system used on the V6 engine retards the spark advance when detonation occurs. The retard mode is held for 20 seconds, after which the spark control will revert back to the electronic spark timing or EST control of the ECM. The ESC system uses a knock sensor to detect the presence and intensity of the engine detonation or spark knock. The knock sensor is mounted in the right-hand side of the cylinder block, just behind the oil pressure switch. The output of the knock sensor is an electrical signal, which is sent to a controller which is mounted on the ECM memcal. The controller processes the sensor signal into a command signal to adjust the EST. The process is continuous, so that any presence of detonation is monitored and controlled. The ECM has a built-in factor and knows exactly what timing degrees are required to retard the timing of the engine. Fail-safe features.
To reduce the possibility of any vehicle being immobilised due to a malfunction in the engine management control, each critical circuit in that system has a parallel backup. In fact, we've already discussed two of these backup circuits, the fuel pump relay and the spark timing bypass mode. If the ECM actively detects a faulty sensor, it will substitute a value for that particular input. The following examples are indications of those substitute values. A throttle position sensor problem will be overcome by the ECM substituting a value based on engine speed. A manifold absolute pressure sensor malfunction will trigger a substitute value based on throttle position sensor input.
Diagnostic system operation. The GMP4 has a sophisticated self-diagnosis and backup system if any part of the system breaks down or fails. The check engine light is mounted in the instrument's warning lamp bar and has two functions. It is used to tell the driver that a problem has occurred with the engine and that the vehicle should be taken to the nearest Holden dealer as soon as possible, and it is used by the technician to read the malfunction codes to help diagnose any problems the system has developed. As a bulb and system check, the check engine light will come on when the ignition is turned on. When the engine is started, the check engine light should go out. If it remains on, the self-diagnosis system has detected a problem. Diagnostic connector. To extract malfunction codes from the ECM, we use the assembly line diagnostic link, or ALDL. This diagnostic connector is different from any other connector previously used for checking the system. The ALDL connector is located here on the left-hand side kick panel near the ECM.
When the ignition is turned on and the engine is not operating, the check engine light is illuminated by a feed from the ECM. When the engine is started, the ECM turns the lights off, indicating that there have been no problems located at that time. If the ECM does detect a problem, it will turn on the check engine light and keep it on for a minimum of 8 seconds, or as long as the problem exists, storing a trouble code in its memory. This trouble code will stay in the memory until battery power is removed from the ECM.
Reading malfunction codes. To read malfunction codes, use a modified SD28079 diagnostic link to earth out the AB test terminal. That's circuit number 451. With the engine stopped and ignition on, the ECM will enter into the diagnostic mode. The check engine light will now flash out any trouble codes stored in the ECM memory. If there are no malfunction codes, then the ECM will flash a code 12. That's one flash, pause, then two flashes. If, say, a code 34 was present, the sequence would be 3 flashes for 30, pause, then 4 flashes, giving us a code 34. Each code will flash 3 times, working from the lowest number to the highest. To avoid confusion, no new codes can be stored while the system is in the diagnostic mode. Also, all relays and solenoids controlled by the ECM are energized. The IAC motor is pulsed and the engine cooling fan will operate. If the engine is started with the diagnostic terminals bridged, the ignition timing will be fixed at 10 degrees before top dead center until engine speed reaches 2000 RPM. If a problem occurs, say through a poor connection, and then corrects itself, the light will switch on for 8 seconds and then turn off. But the trouble code for that malfunction will still remain in the memory. Such malfunctions are known as intermittents, which may or may not reoccur. The ECM will continue to monitor that circuit, and if the malfunction does not reoccur within 20 engine starts, the trouble code will be erased from the ECM's memory. Field service mode. When the ALDL is earthed and the engine is running, the check engine light will no longer flash out malfunction codes. Instead, it will be indicating the open and closed loop fuel control at the engine system. Let's take a close look at this field service mode. Flashing open loop means the check engine light will flash on and off 2.5 times per second. That's 5 times every 2 seconds. Flashing closed loop. With fuel system operating normally, the check engine light will flash on and off at a rate of once per second. Flashing closed loop. The oxygen sensor input is indicating a lean mixture. The check engine light will be off all or most of the time. Flashing closed loop. The oxygen sensor input is indicating a rich mixture. The check engine light will be on all or most of the time. Diagnosis. The service manual contains a number of flowcharts which have been designed to guide you through a logical procedure to locate a problem in the system. The right-hand page gives you a step-by-step diagnostic tree chart with some additional information for that specific trouble code diagnosis. The left-hand page, used in conjunction with the diagnostic tree chart, gives you a brief description of the circuit and/or specific sensor operation in the system, including operating parameters. Also included are explanations relating to the numbered boxes on the diagnostic tree, giving you valuable additional information on what you are checking and why. If a problem arises, all you need to do is begin with the diagnostic circuit check page and then follow the simple procedures that have just been outlined. In this way, the cause will be found with a minimum of time and inconvenience to the customer. Reference to the diagnostic charts will show that low electrical values are often quoted. The only efficient way that these values can be measured accurately is to use a digital multimeter of a similar type to the one you see here. It must, however, have an impedance of 10 megohms to ensure accurate readings. This completes this segment on the engine management system as fitted to the 3800 V6 engine. The second tape in this package includes information on the Delco throttle body injection system, catalytic converters and oxygen sensors.